Assalamualaikum and very good morning to all. So as I mentioned in the class group, I'm so sorry for today's class. We have to cancel. But however, I replaced with the recorded lecture for you guys. Alright. So for today's attendance, please scan this QR code. Right. So I hope this QR code is working. All right, so if you have problem to scan this QR code to record your attendance, please let me know. All right, okay, so we will continue to the next chapter, which is the magnetostatic field. Okay, so we have finished the electrostatic field in our previous class. All right, so for today we will continue the next chapter, which is a new field, which is the magnetostatic field. All right, so in this magnetostatic field there are two laws that you need to know, which is the Biot-Savart's law. All right, or also known, or we called it as BSL. Yeah, BSL. Right, Biot-Savart's law. All right. Okay, so now let's look into detail the introduction of magnetostatic field. All right, so magnetostatic field, it stands since that the magneto here, it stands that in this chapter we only discuss the magnetic field. All right, we ignore the presence of electric field. All right, and okay, so if in electrostatic field, okay, we have calculated E, right, which is the electric field intensity. However, in this magnetostatic field, you will be calculating the magnetic field intensity, which is represented as H, and also the magnetic field density, that will be represented as B. Okay, so you should be familiar with this and this. Okay, we're gonna have throughout this field, throughout this magnetostatic field, you will always come into determine H or B. If you know your H, you can determine your B. If you know your B, you can determine your H. All right. And then the static here, okay, the static here means that this particular field, okay, is independent of time. So there are no time variation in this static, in this field. All right. So when you are discussing in Cartesian, for example, your H in a Cartesian, it will be only in X, Y, and Z form. Okay. And if it is in cylindrical, it will be only in R, V and Z form. And if it is in a spherical, it will be R, V, and theta form. Okay, so there are no included of time in this particular field. All right. So these are the introduction, or the clarifications of magnetostatic field that you need to know at the beginning of the chapter. All right. So now let's look what are the sources. Okay, what are the sources of the moving charges? All right. What are the sources of magnetostatic field? Sorry. So the sources of the magnetostatic field will be moving charges. So it's contradict, or it's quite different from electrostatic field, where for electrostatic field the sources is static charge. Okay, static charge in electrostatic. Okay, electrostatic. But for magnetostatic, it is a moving charge. So when we say it is a moving charge, okay, we will discuss it, or we will call it as in terms of currents. Okay, so the currents will be represented as this. Okay, I believe you still remember what we have. You have looked this equation before. Okay, which is the current density J is equals to rho V and U. What is U? U is the apa namanya? U is the speed. Okay, U is speed. So okay, so this is the current density. Okay, this whole equation is known as current density equation, and U, which is the speed of the current. Of course, yeah, when the charge is moving, it must move with with a value of speed. There must be a speed to allow that the charge to move. And in this field, in this magnetostatic field, we assume that the U, okay, the U, which is the speed, is always constant. So when U is constant, can you guess what will become zero? The acceleration. Okay, the acceleration will becomes zero. Okay, when U, the speed is constant, of course the acceleration will becomes zero. And therefore, when the acceleration is equals to zero, we assume the source, okay, or the source that will be applied to this magnetostatic field is in a DC current. Okay, the moving charge is moving in a DC current. Okay, where the speed is constant, the acceleration is equals to zero. All right. So now you have to suit this current density into three types of model. Okay, into three types of charge model, which is the filamentary current model, surface current model, and volume current model. All right, so now we want to suit this equation, this charge or current density equation, into these three types of model. Okay, charge model. All right, so the first thing is a filamentary current. Okay, filamentary current, or it is also known as line current. So line current, okay, let's assume that this is a line current, okay, or we can also call it as filamentary current. So for this line current, okay, we assume that the currents flow, okay, the total of current flow in this line current is equals to I. This is the total of current flow inside this filamentary current. And let's take a sample. Okay, same as electrostatic field, we will always taking sample. Okay, so if we are taking sample here, okay, which is filamentary current element or sample. Okay, so to calculate this sample, okay, it is I, the total of currents that flowing inside this line current, multiply with this DL, the sample. Okay, this distance here, the sample distance, which is DL here. So it will be I multiply with DL, and the unit will be ampere meter. This is ampere, current is ampere, DL is meter. So the unit will be ampere meter. Alright. So for surface and volume, let's look for surface and volume. So let's assume that this is a surface, a sheet. You have a surface, for example, like a paper, a very, very thin paper. Okay, and let's assume that the currents flowing inside this is represented as Js. So J is the current density, S is represent the surface, yeah, the surface current. So now, same as before, let's take a sample of it. So this is the sample that we want to calculate. Okay, the sample that we want to calculate. okay, the sample that we want to calculate. So how to calculate the sample? So it will be the total of currents that flowing inside surface, which is JS. You have to multiply with the sample area, which is DS. So JS usually will be in a units of ampere per meter, and DS will be in a unit of meter squared, and therefore the unit for this sample area, it will be ampere per meter, because this and this you can cancel out each other, so the unit will be ampere meter. All right, and now so that is for surface. And now let's look for volume. Okay, for volume, let's assume that you have like a cord of wire. Okay, a cord of wire like this. Okay, and you want to measure the volume current inside this structure. Okay, assume that the total current density flowing inside this structure is represented as J. Okay, J. So therefore you want to calculate this sample area, this sample. All right, so same as before, J, which is the total current, you have to multiply with dV, because this is a volume, right? This is a volume structure. So it will be J, usually it is in ampere per meter squared, and dV usually is a meter cubic, and therefore you will get, yeah, your results. This sample have a current has a current as ampere per meter. Okay, ampere per meter. So these three, what is it? Okay, these three elements, or these three models of current, okay, these three models you have to memorize. Okay, because usually in your final exam, because magnetostatic field will be asked in your final exam. Okay, so usually the first question of magnetostatic field is about fundamental question, which is about your basic knowledge. So the basic knowledge, usually they will ask about this. Okay, describe the charge model for electrostatic field in terms of filamentary current, or in terms of surface current, or in terms of volume current. So in order for you to explain that, you have to know this currents model. Okay, you have to know this currents model, and you have to able to explain it in exam. Okay, so in exam, if you think that a diagram like this will help you to explain, so you also allowed to draw this diagram in your exam, okay, to help you to explain or to describe your answer. All right. Okay, so don't take for granted for this part, yeah, because this part usually it will be asked in your first question. It is a fundamental questions. Okay, now let's look about the source and the field here. Okay, the source and the field, the relations of source and field. Okay, so in electrostatic field, okay, our source is usually represented as rho v. Okay, our source is usually represented as rho v, and if you want to calculate the electric field intensity, we are usually use Coulomb's law, right? Still memorize it, yeah. We usually using our Coulomb's law to calculate E, and the Coulomb's law give to us this equation, which is, in order for us to calculate the sample of the from the sample, if you want to calculate the electric field intensity, so it will be sample multiply with the unit vector, okay, of the sample to the electric field intensity over 4 pi epsilon r squared. So this is what we have learned before. So since I said that magnetostatic field is just an imitation of electrostatic field, however the source is different. So we're going to use the same application for magnetostatic field, the same concept here. So now in magnetostatic field, our source is J, which is the moving charge, yeah, current density J. And let's say we want to determine our H. Okay, we want to determine our magnetic magnetic field. All right. So if you want to determine your magnetic field, okay, by with your source here, so we will use our Biot-Savart's law. Okay, we have to use our Biot-Savart's law, and Biot-Savart's law, okay, give to us, okay, Biot-Savart's law tell to us dH, which is the sample, okay, the sample. If you want to measure the sample dH, for example, in this case here, for example, in this case here, in this case, you want to measure the magnetic field. Okay, let's say that you have a magnetic field somewhere in this structure and you want to measure the magnetic field. So from this sample, so from that sample, okay, dH is equal, you want to measure the sample magnetic field, so it will be the sample cross product, yeah, sample cross product. So this is different between electrostatic field and magnetostatic field. In electrostatic field, it is usually dot product, right? But in magnetostatic field, it will be cross product. There is no dot product anymore. Sample cross product with the unit vector, okay, of the sample to that particular H field over 4 pi r squared, okay, over 4 pi r squared. And let's say this sample now you are dealing with the volume structure, so you have to replace the sample to the volume structure just now, okay, the volume structure just now, JdV, right? So for volume structure, you just have to replace the sample with JdV cross product with the sample with the unit vector of the sample. Okay, and let's say you are dealing with the current, filamentary current or line current, so you have to replace the sample with IDL. And if you are dealing with the surface current, so you have to deal with you have to replace with JSDS. All right. So now, I didn't include inside this slide the meaning or the definition of the Biot-Savart. Okay, so the definition of Biot-Savart, okay, you can look in your book. Okay, for example, in your soft copy book here. Okay, you can scroll to the page of okay, to this page, all right, to the 325, page 325, there is a definition of Biot-Savart's law. You also need to know this explanation, yeah, this definition of Biot-Savart. So Biot-Savart's law states that the differential magnetic field intensity dH produced at point P as shown in figure 7.1. Okay, this is figure 7.1. I'm not sure why there is a black here. Okay, I'm not sure why there is a black here. Okay, usually if you have your book, it's not supposed to be black here. So this is the point P. Okay, this is a point P, and this is the currents. Okay, so these are the sample area. Okay, this is the sample area. So the sample area is DL. And okay, so the DH, so now you want to measure the DH from this sample to this point P. Okay, so this definition states that DH, which is the magnetic field intensity, produced at point P, okay, produced at this point P, by the differential current element IDL is proportional to the product IDL and the sine of the angle alpha. So there is an angle here, alpha. Okay, sine of the angle alpha between the element and the line joining P to the element, and inversely proportional to the square of the distance r between P and the element. Alright, if you look properly to this definition, I know it is quite long. It is actually describing, okay, this definition is actually describing, okay, describing this formula, okay, which is, so now the sample is representing as IDL, okay. They assume that the sample now is in a filamentary current element, so it is represented as IDL. So IDL multiply, okay, sine alpha here is actually, okay, sine alpha here is actually the unit vector. Okay, this is the sine alpha. It is actually the unit vector of this sample to this point, okay, over unit vector area over 4 pi r squared. So if you are unable to memorize this definition, however, if you understand this formula, okay, you can also describe this formula in your own words, which is dH is proportional sample multiply with the unit vector, okay, cross product of sample with the unit vector, and inverse proportional to the 4 pi r cubic, okay, inversely proportional to the square of distance, okay, to the square of distance r, to the square of distance of the sample to the unit vector. Okay, so don't worry if you can't memorize this definition, but as long as you know this formula, try to describe this formula in your own words as well. All right. Okay, so look the definitions of Biot-Savart in your book. Yeah, I didn't put inside this slides. Okay, so now let's look to this to this example. Okay, so I have some of this wait, yeah. Okay, so just now I just erased all the intonation that I have made before. So this is example 1. Okay, let's look to this example. Example 1, the question asks, find H for the finite line current. So this is the finite line current, yeah, because you know the A and B. Okay, it is a very finite A and B. It is not infinity. You know the distance. Okay, and what the question asks, you have to find H for the finite line current. So let's assume at this the total of currents that flow for this line current. So this is a line current, yeah, line current, or also known as filamentary current. Okay, filamentary current. So let's assume the currents flow, the total of current flow inside this line current is equals to I, all right? And they ask you to measure the H. So there are steps that you have to follow in order for you to solve this example. Okay, so the first step, you have to recognize which of the orthogonal coordinate systems that suits this problem. So by right, I think you should already recognize, yeah, which orthogonal coordinate system that suits in this matter. So which orthogonal coordinate system that you think? So in this case, the orthogonal coordinate system that suits in this example will be cylindrical. Okay, so this is same as our electrostatic field. Okay, cylindrical. All right, so if it is in terms of cylindrical, the coordinates that we're going to deal with will be r, v, and z. So these are the variables of coordinates that we will deal with. Yeah. And then the second steps is where are the location of field. So you have to determine where are the location of field that you want to put inside this structure. It can be located here, it can be located here, it can be located anywhere. So in this case, I assume my H to be around this position. This is my H. Okay, so this is my H, and then you have to number 3, step number 3, you have to take sample anywhere on the line current. So your sample must be located anywhere on your line current. It must located on your line current here. So let's assume I want to take my sample here. This is my sample. Okay, this is my sample. So the ink is same ink here. I want to change my ink. There is a down part here. Can I? Okay. I can't remove this part. Yeah. How to? But it's okay lah. Okay. So this is gonna be my ink. Okay. Oh yes, I can remove that. So I erase this. I'm gonna use a different ink. Then I'm gonna use this ink. Okay, so that you can identify where the sample, you can differentiate. Yeah, so this is my sample. Okay, sample anywhere on the line current, so it can be located down here, it can be located up here, so no problem. Yeah, as long as it is lies on this line current. Yeah, and then what you have to do, link the sample to the field. So what you have to do, you have to link this sample to this particular field. All right, so this is your will be your R unit vector. Okay, so this is your R then. Yeah, okay, so now the formula said to us, okay, the formula using Biot-Savart, yeah, the formula said to us dH, which is the sample area, the magnetic field of the sample area, is equals to, since that this is a filamentary current or line current, so it will be I dl, right? I dl cross product unit vector R over 4 pi R squared. Okay, so this is the formula of Biot-Savart. Okay, now what you have to do, you have to identify the IDL first. Okay, to identify your IDL, you need to know the distance. Okay, so now let's assume, okay, the distance of this H field to this X and Y axis. So we are bringing the H field, okay, to this down part, and we want to connect it with this X and Y. So this will be our phi. Okay, this is going to be our phi, and the distance, the height from here to here, the height from H field to the X and Y plane, let's represent it as Z. Okay, I represent it as Z. And then the height of my sample, this is my sample here. The height of my sample, okay, from the Z axis, yeah, from the origin to this sample, it will be my Z prime. Okay, I make it as my Z prime. And then if I'm taking my H, I connect my H to my line current orthogonal, okay, 90 degrees, yeah, my H, I connect it to 90 degrees to my line current, and I represent it as R. Okay, this is my H. I connect my H with the line current. It must be 90 degrees. Okay, so the distance will be R. Okay, the distance will be R. Okay, so now I will going to use all this information to this Biot-Savart formula. Okay, so I have to determine my IDL first. Okay, so what will be my IDL? I is the total current, so the total current that flowing inside here is I, right? So it will be I. Okay, I. Why it is I? Because the total current flowing inside here, I mentioned earlier, it is I. So it's same, yeah, I. Okay, what is going to be my DL? My DL will be the sample here. Okay, so the sample here, and this is my sample. So my DL will be dz prime, right? dz prime, the height of this sample here. Okay, dz prime at which direction? On a z-axis, because my sample lies on a z-axis, right? So it will be on z direction. Okay, so this is my IDL information. Now I need to have, in terms of unit vector, I need to know my vector R first, right? So my vector R will be R at R direction, R at R direction. Yeah, this is R direction. The radius, yeah, R at R direction minus, because it's going down, yeah, the sample is going down from the H, so it's minus. So my H, the height of H, it will be Z prime minus Z, right? Z prime minus Z on Z direction. Okay, I hope this one you clear, yeah? R is going out, yeah, R direction, positive direction, yeah, because it goes in this way. And then in Z direction, our H is located slightly down compared to this sample. So it will be Z prime minus Z. So it will going to be in minus Z directions, yeah. So therefore, we have all the informations here. We can go inside, we can replace inside and substitute inside this equation. So to substitute that, our DH then, it will be I dz prime at Z direction, cross product, yeah, cross R at R direction minus Z prime minus Z on minus Z direction, yeah, over 4 pi R squared plus, so if you know your R vector, your R will be R squared plus Z minus Z squared, square root of it, right? So R squared plus Z prime minus Z squared. However, this is unit vector, yeah? So unit vector, if you still remember, A R is R over R, right? R over R. So this R multiply with this R, so it will be cubic R, right? So it will be 3 over 2. And this R is square root R here, yeah? So it will gonna be 3 over 2. Okay, now, what are the next step that you need to solve this? You have to solve this cross product. Okay, so Z cross product with R direction. Okay, so this is not dot product, yeah? Z cross product with R direction. How to solve that? If you still memorize, Z R and then phi. Are you still memorize this? We discussed this when at the beginning of the chapter, at the vector cross product vector. Is usually it's represent as Z, X and Y. Okay, where Z, X and Y, so this gonna be Y, this is gonna be Z, and this gonna be X. So Z cross product Y, your Z cross product X, sorry. For example, yeah, Z direction cross product X direction, you will get Y direction, yeah, and then X direction cross product with Y direction, you will get Z direction. So I just replace X and Y with R and phi inside here. So here we're going to be phi, here we're going to be R, here we're going to be Z. Okay, so now in this case, you look here, Z cross with R, Z cross with R. So it will be phi product, phi direction, phi direction. Z product cross with R product, it's going to be phi direction. Next, Z direction multiply with minus Z. Okay, don't forget the minus in front here, yeah? Z multiply with minus Z. So Z multiply with minus Z. So it will give us 0. The same direction for cross product, it will give us 0. So it is opposite with dot product. If dot product the same, for example, X dot X, you will get 1, right? But in cross product, X cross X, you will get 0. Okay, so be careful for that, yeah? So therefore, there are no Z axis, yeah? There are no Z direction, sorry, not Z axis, but no, Z direction. There are no Z direction because Z direction cross with minus Z direction, it will becomes 0. So therefore, after you solve your cross product, you will get I, R, the R is still exists here, yeah? I, R, dz prime, and now in which direction? It will be in phi direction, okay, over 4 pi r squared plus z prime minus z squared 3 over 2, okay. So this is your dH. Alright, so to get your total magnetic field, your H, it will be, what you have to do? You have to do integrations, right? So it will be IR over 4 pi phi direction integrations of dz prime over r squared plus z prime minus z squared 3 over 2, 3 over 2. So what are the limits? The limits will be the limits here, A and B, A, B. So therefore, you will then get your results, yeah? Your answer will be, if you solve this, okay, you will get your answer. It will be, try to solve this, yeah, in a phi direction, I over 4 pi r b minus z over square root of r squared plus b minus z squared minus a minus z over r squared plus a minus z squared ampere per meter. Okay, so this is your final answer. Okay, so this is your final answer. All right. Okay, so okay, all right. So now let's look this same question in terms of graphical approach. Okay, graphical approach. So I want to redo this question in terms of graphical approach. Okay, for example, now let's redraw these equations. Yeah, I'm going to use different ink. Okay, so this will be my filamentary A and B. A, B. This is my filamentary line current, yeah, AB. And my location of H is located at here. This is my location of H. Alright, so the total of current flow inside here is I. Okay, current flow inside here is I. And then what else? So okay, so you know the total current of current flow inside here is I, and this is the location of H. So now let's connect, yeah, this A and B to this point H. So if we connect those, which color should I use? I'm using green. Sorry. Here's part, yeah. Okay. Alright, so I'm connecting my A and B to point H, yeah. Okay, please assume this is a straight line, and then to B as well. So now from here, okay, you can see this is like a triangle here, yeah. And then if H, you can see we are taking a straight line from the line current to H, yeah. So this is the orthogonal line, right? Normal line. So now we're gonna do the same thing. Alright, so this line is represented as R, okay, in R, and therefore, okay, from this, let's assume, okay, the H here, the height for here to here, okay, the height from the H normal to the line current from the E is given as Z, alright. So therefore you can calculate, or you can determine the height of A until this normal line to H. So what are the heights here? So it will be Z minus A, right? Z minus A, the height here. And this height will be, I think by right you should guess, you are already able to guess, right? B minus Z. So this is the height for this part, and this is the height for this part. All right. So A plus B, from A to Z minus A, Z minus A is this height. B minus Z is this height, right? So you know this height, you know this height. Can you measure this height? Of course, yes, right? Using a theorem Pythagoras, if you still remember maths, yeah. So it will be square root of R squared plus B minus Z squared, yeah, B minus Z squared, and this part it will be R squared plus Z minus A squared, right? Okay, now, if you look at this part and this part, okay, this part and this part, all this same, this parameter is also exists in this parameter, right? B minus Z R squared, B minus Z is this part. So therefore from here you can get the angle here, which is alpha 2. Let's assume this is alpha 2, this is alpha 1. So alpha 2 able to be represented, this one, yeah, B minus Z over R squared plus B minus Z squared. This is actually sine alpha 2. Yeah, if you still remember your trigonometry. And for this part, R squared this is Z minus A, right? Z minus A. However, this one minus, the minus is this part. This is Z minus A, and this one is A minus Z. So this is macam the other way around, right? So how to make this form into this form? So what you have to do is you change. You bring the minus inside here. So if you bring the minus, so this will gonna be this one. It will become positive. So and this 2 will become Z minus A. Are you agree with me? You bring inside here Z minus A. So in front here will be positive, and the behind here will be Z minus A, which is the same form as this one, right? And the down part you don't have to change, because A minus Z or Z minus A, you are square rooting, you are squared this part, eh? A minus Z, for example, let's give a value. A minus Z is equals to -2. I give you example, yeah, and then z minus a is equals to 2, and if you square this 2, you will get the same answer of 4. So you don't have to rearrange this down part, because this is square. Okay, your final answer you're gonna be the same. So this one, if you change it, z into z minus a, so this will gonna be sine alpha 1. So therefore, you can simplify this equation to be I over 4 pi r sine alpha 2 plus sine alpha 1. Alright, and this is actually the formula. This is actually formula for line current, for filamentary line current. Alright, line current, don't forget the units here, ampere per meter. Alright, so this formula, although this is a formula, yeah, this formula will not be given during your exam, so you should either you memorize this by your heart, or you know how to solve this from the beginning of the solution. Alright, so there are two ways. Either you know how to, but I will suggest you to know to understand the methods, yeah, instead of memorizing this by heart. Okay, so now let's assume, okay, this is for the finite line current, where you know the distance A and B. Okay, you know the exact distance A and B. For the infinite line current, so for the infinite line current case, so the A and B will be infinite case, yeah. So your H will be P direction I over 4 pi r. We're going to use the same one, plus sine alpha 1. So in an infinite line current, look back to this chapter, to this question. For the infinite line current, so this is going to be very, very long, right? This is going to be very, very long. So therefore, the angle here, the maximum angle here is 90 degrees. Okay, the 90 degrees, yeah? The maximum angles here, it will be 90 degrees, because it's going to becomes straight line here, right? So for sine, so therefore your alpha 1 will be equals to alpha 2, which is the value is 90 degrees. So if the value here, you can try using your calculator, sine 90 degrees, it will give you results as 1, right? So I over 4 pi r 1 plus 1, and then you can cancel this, it will becomes 2. So therefore straight away you will get this answer, yeah, on the phi direction I over 2 pi r. So for the infinite line current, these are the formula. Okay, these are the formula, right? So this formula also will not be given in your formula list during your exam. The only formula that will be given to you for in your exam list will be this formula. Yeah, where is it? Yeah, only this formula, yeah, sample multiply with AR over 4 pi r squared. Okay, only this formula that will be provided to you. So therefore you have to memorize, you have to understand these calculations. Yeah, for the infinite line current, you can straight away use this formula, and for the finite line current, you can straight away use this formula. All right, so now let's look another sample. Okay, I want to erase this all the annotations that I've made here. Okay, so now let's look another questions here. Find H along the z-axis. Okay, so this is the z-axis. I forgot to. Okay, this is x and this is y. Alright. So let's assume that the currents flow inside here is a clockwise current. Okay, a clockwise current. So it's anti-clockwise current. All right, anti-clockwise current. Okay, so in this direction, yeah, anti-clockwise directions, and the total current flow inside here is I, and this is a tube, for example. It's just like a tube, just like a wire, okay, but in a circle shape, yeah. Okay, a wire like a circuit shape, yeah. So what they ask to you, find H along the z-axis. All right, so we're going to use the same formula, Biot-Savart's formula. So this is going to be dH is equals to IDL multiply with AR over 4 pi r squared. Okay, so what at the answer? So from the diagram, okay, first of all, what you have to identify, you need to identify the IDL first. So to know the IDL, you should take a sample. Okay, so let's assume your sample is located at this part, and then you should have your locations of H, right? So let's assume that your locations of H is located at here. So your location of H must be along the z-axis, any point as long as it is lies on z-axis, yeah? So this is my H field, this is my H. And then what should I do next? If you still remember the steps, I have to connect, right, this point, this sample to this H. So let's connect it. Okay, all right. So this is gonna be my R. Okay, this is gonna be my R. So therefore, my IDL will be I. So I, because the total currents flow inside here is I. So my I is I. So what is my DL? My DL will be R d phi. This is my sample, right? I d phi on phi directions, right? Because this is lies on xy plane, so you're gonna be on phi directions, yeah, d phi. Okay, now my R, they already mentioned to us, is equals to A. The radius is equals to A. So therefore, my IDL is equals to I A d phi on phi directions. Okay, on phi directions. Next, you know your IDL already. What is your unit vector? So to form your unit vector, you need to find vector R. So vector R will be, so this is your point of H. So therefore, it will be at R direction, minus R directions, yeah? R at minus R directions. So your R is equals to 1. The radius is A. So instead of write your R here, you can write A. Okay, you can write A because we know the radius is A, right? A at minus R direction because it's going back here. And then plus, you're not arrived yet your H, right? It will be Z on Z direction. Okay, so you know your informations of unit vector. So what is your R, your distance? It will be square root of A squared plus Z squared. All right, so you know all the informations already, so you can substitute inside the equations. So your DH will be equals to I A d phi on phi direction cross product with minus AR. I bring the minus in front, yeah? R. Okay, okay, wait, yeah. R plus Z at Z directions here over 4 pi. Okay, 4 pi. And then A squared plus Z squared 3 over 2. Okay, so now what we have to do is we have to solve the cross product then, yeah? So the cross product A at phi with minus R direction. So don't forget the minus here. P cross product with minus R directions. What are the directions? The directions will be on Z directions, yeah, Z directions. And then P cross product with Z directions, you will get R directions. Okay, so memorize again, yeah, revise again this cross product if you are not so sure about this. Okay, okay, next, what you're gonna have after you solve this, it will be AI, A, D, Phi, and then A inside here, it will be on Z directions, plus Z inside here, it will be on R directions. Okay, over 4 pi squared Z squared 3 over 2. Okay, now you have both Z and R directions. Okay, if you still remember, if you have a D's, okay, if you have a D's, what you have to do, if you still able to recall again in your electrostatic, it will cancel each other, right? So therefore, let's assume inside here, okay? I'm drawing inside here. I'm drawing on my x-axis here, okay, on my x-axis here, where this is my z-axis, okay, z and x-axis, yeah, this is my y-axis, okay. I'm looking from my eye is located at this part. So at this part you can see the currents is going in, okay, the currents, I'm using different color lah, yeah? I'm using different color so that you can differentiate. So this is my x-axis. Okay, at this part, this is the currents we are looking at here. Yeah? At this point, the current is going in, so it's gonna look like this, right? And then at this point, if you make the long axis, at this point, the current is going out, right? This is the positive x direction. This is the negative x direction. The current is going out at this part, right? So my sample area is located somewhere. Okay, let's assume my sample area is located at this part. So at this part, so this is my H field. Where is my H field? This is my H field, right? This is my H field. So now this is my sample. This is my sample here. If you still remember, the sample here, there's another sample that opposite to this sample. There's always another sample that opposite to this sample. Okay, so it is this sample, yeah? This is the sample, the sample that I'm taking here. This is the opposite sample at this point, okay? All right. So if I'm connecting this one to my H, all right? So this is my field, my H field, right? My H field in respect to this sample. So if we can separate this component, the component of my H field for this sample, it will contains of H Z component and H on. Okay, so if you separate this component, it will contains of HZ component and HR component in these directions, yeah, in these directions. And then if we take another sample opposite to this sample, which is this sample, if we can, I'm using different color, yeah, if we connect this sample, sorry, okay, so for this sample, okay, yeah, for this sample, if we connect to this area, okay, so this will be the H field for this sample. This is the H field. So if we separate the component of this H field for this sample, you can see it will have HZ component and the R component is in this direction. So in this case, you can see the R component here, okay, the R component here is actually cancelling out each other because they are in an opposite direction, so they are actually cancelling out each other. But the HZ component at the Z direction here will have here, okay, so it will only have or left behind the HZ component, and the HR component is cancelling out each other. So at this part you can neglect this because it is cancel each other, and it will left only behind the Z component. Alright, so finally this is your DH. So finally, for you to measure your H, it will be on a Z direction. Okay, Z direction. I A squared over 4 pi A squared plus Z squared 3 over 2. And then phi, d phi. So what are the limit for phi? 0 until 2 pi. So if you solve this, you will get your final answer, i.e. 2 A squared plus Z squared 3 over 2. This one we're going to give you 2. Okay, pi you can have cancel there. And then on a Z direction, ampere per meter. I'm so sorry, it's so slanting there. Alright, so this is your final answer. So if you have a circular disc like this, please make sure that at the R component, at the R direction, okay, the R component is cancelling out each other, and it will left behind only the Z component. Alright, so that's all for Biot-Savart. So if you have any question later on, we can discuss during our class. Alright, or if you can't wait until your class, you can also DM me. Okay, PM me any questions or any arguments that you have in your mind. Alright, so thank you very much, and thank you again, class. See you then.